Welcome to the world of non-Euclidean geometry. In this video, we will be exploring curved spaces that go beyond the familiar flat surfaces we often encounter in Euclidean geometry. Get ready to challenge your assumptions about space and shape as we dive into this fascinating branch of mathematics. Let's contrast Euclidean and non-Euclidean geometries. Euclidean geometry deals with flat surfaces where lines are straight, and the rules are familiar, like those you learned in high school. On the other hand, non-Euclidean geometry explores curved surfaces where the traditional rules break down. Think of the surface of a sphere or a saddle shape. The behavior of lines and shapes changes dramatically in these spaces. At the heart of Euclidean geometry lies the parallel postulate, which states that through a point not on a line, there is exactly one parallel line. However, this postulate has been a subject of debate and exploration for centuries. What happens if we challenge this assumption? That question leads us to the realm of non-Euclidean geometries, where parallel lines may not behave as expected. Non-Euclidean geometry isn't just one thing. There are different types, each with its own unique properties. Here we will focus on two main types: spherical geometry and hyperbolic geometry. Spherical geometry deals with the surface of a sphere, while hyperbolic geometry explores negatively curved surfaces. Let us explore spherical geometry. In spherical geometry, lines are great circles on the sphere. These are circles with the same radius as the sphere itself. A key feature of spherical geometry is that no parallel lines exist. Any two great circles will always intersect. Also, the angles in a triangle on a sphere add up to more than 180 degrees. Finally, straight lines on a sphere curve back on themselves, eventually returning to their starting point. Let's look at some examples of spherical geometry in action. One practical application is in great circle routes. These are the shortest paths between 2 points on the Earth's surface, which appear as curved lines on a flat map. Also, consider a spherical triangle drawn on a sphere. The angles of this triangle will always sum to more than 180 degrees, a direct consequence of the sphere's curvature. Let's delve into hyperbolic geometry. In hyperbolic geometry, through a point not on a line, there exist infinite parallel lines. This is a stark contrast to Euclidean geometry. Also, the angles in a triangle in hyperbolic space add up to less than 180 degrees. Another unique property is that lines in hyperbolic space tend to diverge from each other. The space expands exponentially, leading to some counterintuitive results. Let us further understand hyperbolic geometry through surface properties. A saddle surface, which curves up in one direction and down in another, exemplifies negative Gaussian curvature. Another example is the pseudosphere, a trumpet-like surface that exhibits constant negative curvature, embodying the principles of uniform hyperbolic geometry. Non-Euclidean geometry isn't just a theoretical curiosity. It has real-world applications that impact our understanding of the universe. In space and cosmology, non-Euclidean geometry helps us model the geometry of the universe and understand phenomena like spacetime curvature. In navigation, non-Euclidean geometry is used to calculate the shortest paths on Earth's curved surface. This is crucial for flight routes and satellite navigation. In summary, let's recap the key takeaways. In spherical geometry, no parallel lines exist, triangle angles are greater than 180 degrees, and great circles serve as lines. It has positive curvature. In hyperbolic geometry, there are infinite parallel lines. Triangle angles are less than 180 degrees, surfaces are saddle-shaped, and it has negative curvature. Non-Euclidean geometry reveals the rich variety of possible spaces beyond our flat intuition. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.